Welcome to sub-module 3 of 4 on risk management. In this sub-module, we'll explore how structured tools like HARC and HAZOP help us understand, evaluate, and mitigate drilling risks. Our goal is to build a clear framework for identifying hazards, defining consequences, and applying quantitative methods that strengthen decision-making throughout the drilling process. In this session, we have 5 main objectives that will guide our learning. First, we'll understand the use of HARC, hazard analysis, and risk control for separating prevention measures, mitigation actions, and residual risks. Second, we'll apply HAZOP methodology to identify potential causes, deviations, and consequences within drilling operations. Third, we'll recognize the roles of a standard HAZOP team and how each participant contributes to accurate risk assessment. Fourth, we'll evaluate how data quality directly affects the reliability of any risk analysis, looking at what happens when probability or severity values are poorly defined. Finally, we'll apply quantitative methods using probability, spatial analysis, and probability distributions to model drilling risks. By the end of this submodule, you will see how qualitative insights and quantitative methods combine to give a more complete and defensible risk management framework. Let's now begin by working through a practical risk assessment exercise. The HAZOP, or Hazard and Operability Study, is one of the most structured and systematic approaches to identifying risks in drilling and process operations. The methodology begins by specifying the intention of each design section before the study starts. In other words, we clarify what the design is supposed to achieve so that deviations can be clearly identified. The study then looks at parameters that apply to the process. These might include flow, pressure, temperature, or mechanical conditions depending on the stage of the well design. From this structured review, we define possible significant deviations, feasible causes, and the likely consequences. Each of these outcomes is documented in detail, ensuring that the engineering risks of the well design are fully defined. This is critical because HAZOP does not only flag the risks, it also provides a logical framework for linking a deviation to its cause and consequence, making it easier to decide whether changes to design or operations are needed. A key point is that the HAZOP methodology is about turning uncertainty into clearly documented engineering risks. In the next slide, we'll build on this by seeing how HAZOP is used to identify new hazards and improve performance during design changes. A key strength of the HAZOP study is its ability to define both the causes and the effects of potential hazards. By walking systematically through the process, the study improves not only operational safety, but also performance. For example, by identifying potential deviations early, we can design operational safeguards that prevent downtime or equipment failures. When a design is modified, the HAZOP process is repeated. This ensures that new hazards are not inadvertently introduced by changes in equipment, layout, or process sequence. This iterative approach is important because drilling and completions projects are rarely static. Designs evolve, and so must our risk assessments. The HAZOP provides a repeatable structure for that re-evaluation. In simple terms, it acts as a living process for risk control. Each time the design changes, the HAZOP provides assurance that safety and operability remain intact. With this understanding, we now turn to the people involved in making a HAZOP successful, the standard HAZOP team and their defined roles. For a HAZOP study to be effective, it requires the right team structure, with each member contributing specific expertise. At the top, we have the study leader. This is usually someone like an asset manager, engineering manager, or drilling superintendent. Importantly, the leader is experienced in running, has ops, but is not part of the design team. Their role is to ensure the process is followed correctly and impartially. Next is the recorder, often a secretary who captures every detail of the discussion, ensuring problems, recommendations, and decisions are properly documented. Then we have the designer, typically a drilling engineer. They provide technical insight into the design and answer questions about its intent and functionality. Alongside them is the user, often the drilling supervisor, who challenges operability and highlights how deviations may affect day-to-day operations. Specialists, such as senior drilling engineers or service company experts, contribute deep technical knowledge in their respective areas. Finally, the maintainer, usually a drilling contractor representative, ensures maintenance and operational aspects are considered. Together, this multidisciplinary team creates a balanced and thorough assessment of hazards. Having seen the importance of team composition, let's now examine the role of data quality in building reliable risk assessments. To perform a meaningful risk analysis, we must start with a clear definition of both the task and the associated hazards. The task or activity is defined by the drilling process itself, whether that's tripping pipe, running casing, or circulating mud. Once the activity is defined, hazards are assessed based on two factors: the probability of occurrence and the severity of occurrence. Without quantifying both, we cannot perform a true quantitative risk analysis. If we fail to assign probability or severity, the result is purely subjective, which weakens the validity of our conclusions. For example, if a hazard is labelled as likely without statistical backing, it may bias the assessment and drive disproportionate mitigation measures. The strength of any risk analysis is only as good as the quality of the data behind it. By ensuring tasks are well defined and hazards are measured against consistent probability and severity scales, the analysis becomes both defendable and actionable. Having covered data quality, let's now look at a first structured approach to investigating risk, the accident investigation method. The accident investigation approach to risk analysis works by deconstructing what has already gone wrong. It begins with identifying antecedents, the conditions leading up to the event, and then mapping the sequence of events. An events analysis is carried out through quick interviews and wide-ranging investigation across areas such as hole cleaning, well barrier systems, or human factors. The immediate causes are then defined, often traced to substandard conditions or unsafe practices. But to prevent recurrence, we go deeper by repeatedly asking why. This leads us to the root causes, which often fall into categories such as personal or job factors, inadequate system controls, or environmental conditions. Once causes are understood, proposed actions are developed. These may involve controlling standards and practices, correcting systemic flaws, or managing the environment more effectively. The value of this approach is that it turns hindsight into lessons learned, helping prevent repeat failures. However, it is inherently reactive because it analyzes events after they occur. To balance this, our next approach looks forward, integrating risk considerations into design and execution before problems arise. In contrast to accident investigation, the design and execution approach is proactive, embedding risk considerations into the planning phase. The process begins by clearly defining the risk and its potential impact. From there, we ask whether the identified risk could realistically occur on the planned well. This forces us to think critically about applicability. Next, we determine how the risk would be detected in operations, whether through monitoring parameters, alarms, or visual indicators. Once detection is clear, prevention actions and mitigation measures are developed, with contingencies planned ahead of time. Importantly, this approach recognizes that risk management is a multidisciplinary job. Engineers, supervisors, contractors, and specialists must all contribute perspectives to ensure nothing is overlooked. The strength of this method lies in its forward-looking nature, allowing us to design out hazards and prepare for those that cannot be eliminated. With qualitative approaches covered, let's now move into the quantitative side of risk analysis, beginning with the challenge of defining probabilities. When we move into quantitative risk analysis, one of the first tasks is defining probabilities. Typically, we start with a data set from offset wells. For example, let's assume we have data from 10 offset wells. We can count how many times a particular root cause, such as lost circulation or stuck pipe, has occurred. By dividing the number of occurrences by the total number of wells, we generate a probability of occurrence. This gives us an evidence-based probability rather than relying on assumptions. However, a critical challenge arises. How do we apply this probability to our subject well? Conditions may not be identical, and differences in geology, design, or execution could significantly alter the risk profile. This is why probabilities from offset wells are valuable, but must be interpreted with care. They form the basis for quantitative analysis, but they must always be adjusted in context. With probability defined, we next consider whether risk has a spatial component, something particularly relevant when analysing wellbore stability and regional factors. Other methods to improve our probability analysis include moving from one dimension to 2 or 3 and including a spatial component beyond depth. This can allow us to identify the variation in risk probability and severity across the field and update our risk analysis for the subject well related to its position in the field. The figure shows a location map highlighting the 2 wells in green at the top right that didn't exhibit any wellbore stability issues. From this figure, we can start to see there may be a geometric and geological aspect to the wellbore instability identified. The question is, how can we use this information to improve our quantitative risk model for our subject well? The first thing to identify is the location and type of our subject well relative to the offset wells. If it is within the zone of the wells that have had wellbore instability events, there will be increased probability of the occurrence of a wellbore stability event within the subject well. But we have to also consider the geometric aspects. For example, if all the offset wells were J-shape with the instability events occurring at greater than 40 degrees inclination, whilst our subject well is vertical, there may be a reduction in the probability of the wellbore instability risk. The second point is to investigate and identify the reason why the 2 wells furthest from the origin do not suffer from the wellbore instability events seen in the rest. This could be as simple as a failure to report the events or the geometrical well paths. If this is not the case, a discussion with geology may be necessary to determine if there is a geological reason for the difference, such as a fault that results in a change in the far field stresses in the area of the furthest 2 wells. Up to this point, we have analysed probabilities in offset wells and considered spatial distribution of risks. The question now is, can we directly apply these values to our subject well? The answer is not straightforward. While offset data is extremely useful, it cannot always be transferred directly. This is where judgment, context, and conditional probability come into play. A key tool here is Bayes' theorem. In plain terms, Bayes' theorem allows us to update the probability of an event happening as new information becomes available. For example, if offset wells show a 20% chance of lost circulation, but our subject well is drilled in a zone with different pore pressure trends, we must adjust the probability accordingly. By combining quantitative data with engineering judgment, we create a more realistic risk profile. This balanced approach acknowledges both the value and the limitations of historical data. Having established probability and conditional application, we now move into more advanced probabilistic methods, including distributions and simulation. At an advanced level, quantitative risk analysis relies on probability distributions to represent uncertainty more accurately. Not all risks follow the same pattern. For example, some may be best described by a triangular distribution, where outcomes cluster around a central value but still allow for extremes. Others may follow a log-normal distribution, where small values are common but large outliers occur less frequently. Choosing the wrong distribution can lead to serious errors in predicting risk outcomes, so selection must be made carefully. Once the appropriate distribution is applied, we can use Monte Carlo simulation to generate thousands of possible outcomes and see the probability of different scenarios occurring. This provides a powerful decision-making tool, allowing managers to understand not just what might happen, but how likely different outcomes are. The strength of this method lies in its ability to quantify uncertainty in a transparent way. With these probabilistic methods explained, we can now step back and review the objectives of this submodule. As we close this submodule, let's revisit the objectives we set out at the beginning. First, we aim to understand HARC in terms of prevention, mitigation, and residual risk. We've applied this through an exercise that distinguished between these categories and tested whether residual risk was a LARP. Second, we explored the HAS-OP methodology, learning how it identifies causes, deviations, and consequences. Third, we reviewed the roles within a standard HAS-OP team and saw how each position contributes unique expertise to the process. Fourth, we emphasized the importance of data quality, highlighting how probability and severity must be defined to avoid subjective conclusions. Finally, we examined quantitative methods, using probabilities, spatial analysis, distributions, and Monte Carlo simulation to strengthen our risk assessments. Together, these elements provide a robust framework for managing drilling risk. With the objectives reviewed, we're now ready to formally close this session. This concludes Submodule 3 of 4 on risk management. Please proceed to the quiz to test your understanding of the concepts we've covered. Thank you for your attention and engagement throughout this session. I look forward to continuing with you on the final submodule on this subject.